Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your Sumam. We are continuing fluid kinematics. What is fluid kinematics? It is a study of fluid motion without considering the forces which causes the motion. It studies how the fluid flow and how to describe the fluid motion. The topic for today's discussion is velocity, acceleration and flow pattern of fluid particle. The motion of the fluid is extremely complex. Fluid is composed of fluid particles which move at a different acceleration which may change with respect to space and time. So, the motion of the fluid particle in space may be described in three dimensions in the direction of three mutually perpendicular coordinates, that is x, y and z, which is drawn from the position of the particle at any instant of time. Now, velocity is defined as displacement by time. Since it's three-dimensional flow, this velocity has the component in x, y and z direction. So velocity can be represented as ui plus vj plus wk. This I, j, k are the unit vectors in the direction of x, y and z respectively. So u is the velocity component in x direction. That means the displacement in x direction with respect to time, and v represents the velocity component in y direction. That means the displacement in the direction of y with respect to time, and w is the component of the velocity in z direction, which represents displacement in z direction with respect to time. So u can be written as u equal to, it's a function of s comma y comma z comma t, that is equal to dx by dt, and v that is written as dy by dt, and w that is equal to dz by dt. So the resultant velocity that is equal to root of u square plus v square plus w square. The relative position of this fluid particle thus not fixed, and it varies from time to time. So if we are considering the total change in velocity, we have to consider the variation of velocity with respect to space and time. So u that is a function of x comma y comma z comma t. Since u is a function of space and time, the total change in velocity, that is du, that is equal to the change in velocity with respect to space and change in velocity with respect to time. So total change in velocity du equal to dou u by dou x into dx plus dou u by dou y into dy plus dou u by dou z into dz plus dou u by dou t into dt. So acceleration component in x direction equal to the total change in velocity in x direction with respect to time. So ax represents the acceleration component in x direction equal to du by dt, that is equal to dou u by dou x into dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt plus dou u by dou t into dt by dt. So what is dx by dt? It is the velocity component in x direction, and dy by dt is the velocity component in y direction, and dz by dt that is the velocity component in z direction. So correspondingly dx by dt that is equal to u, and dy by dt that is equal to v, and dz by dt that is equal to w. So if you are substituting the corresponding values of dx by dt and dy by dt and dz by dt, then the expression for ax can be written as ax equal to du by dt, that is equal to, this term is replaced by u. So u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. Correspondingly, we can write down the expression in y direction and z direction. So ay equal to dv by dt, that is equal to u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. Similarly, we can write down the expression for az, that is the acceleration component in z direction. The resultant acceleration can be written as root of ax square plus ay square plus az square. So the acceleration component in x direction and y direction and z direction, which includes the change of velocity with respect to space and change of velocity with respect to time. So convective acceleration means the acceleration due to change of velocity with respect to space. So local acceleration means acceleration due to change of velocity with respect to time. We can detail it by solving a problem. So the velocity along the central line of nozzle of length L is given as u equal to 2t into 1 minus x by 12 the whole square, where u is the velocity in meter per second, t is the time in seconds, and x is the distance in meters from the nozzle inlet. So we have to find out the convective and local acceleration when t equal to 1.5 seconds and x equal to 0.2 meter. And the length of the nozzle is given as 0.5 meter. So the velocity is given as the function of x comma t, which represents one-dimensional flow. So the expression for convective and local acceleration can be written as ax equal to u into dou u by dou x, which represents the spatial variation of velocity, and dou u by dou t represents the local acceleration, that is acceleration due to the change of velocity with respect to time. So expression for the velocity component u, that is given as u equal to 2t into 1 minus x by 12 the whole square. So at the time t equal to 1.5 seconds and x equal to 0.2, then u can be calculated as u equal to 1.92 meter per second. And the expression for convective acceleration is equal to u into dou u by dou x, u into the differential of u with respect to x, so that is 2t into x by 12 square minus 1 by L. So if you are substituting the values of time, x and L, then the convective acceleration obtained as minus 9.216 meter per second square. And the expression for local acceleration is given as dou u by dou t, that is the differential of u with respect to t. So if you are substituting the corresponding values of t and x, then local acceleration obtained as minus 1.28 meter per second square. So you can very well work out this problem and verify the answers. Next part of this session is the discussion on the flow pattern of fluid particle. Pathline is defined as line traced by the fluid particle during its course of motion. At a particular time t1, the position of the fluid particle is A. When the time progresses and when time equal to t2, this fluid particle moves from this position to this position. And when the time increases further and when the time equal to t3, this fluid particle moves to this position. So if you are joining all these positions by means of a line, it represents the path line. Or path line is the path or curve traced by the fluid particle during its course of motion. So it gives instantaneous direction of the velocity. Whereas streakline is the line traced by the fluid particle passing through a fixed point in the space. For example, if you are injecting dye in a liquid, or the line formed by the smoke particle ejected into atmosphere from a fixed nozzle forms the straight line. Suppose these colors represents the initial position of the fluid particle, or this is the station point from where we are ejecting the dye or smoke. So after some time t, these four fluid particles will occupy this position. If you are joining this particle by means of the line which represents the streak line, or streak line is defined as the line traced by the fluid particle passing through a fixed point in the flow field. So we can differentiate path line and streak line. Path line is the line traced by the fluid particle during its course of motion, whereas streak line is the line joining the fluid particle passing through a fixed point in the space. However, in steady flow, both path line and streak line both are same. So next part is the discussion on streamline. Streamline is the imaginary line or curve which we can draw in the flow field in such a way that tangent to any point in the line will give you the direction of the velocity at that point. So let us consider a point here in a two-dimensional flow fluid. So this curve represents the streamline. This is a point on the streamline. So if you are drawing a tangent at this point, it gives the direction of the velocity. Since it is a two-dimensional flow, this velocity has the component in x and y direction. So u is the component of the velocity in x direction and v is the component of the velocity in y direction. And theta, that is the angle made by this tangent with respect to horizontal. So what is tan theta? Tan theta, that is equal to v by u, or tan theta equal to dy by dx, that is equal to v by u. We can modify this equation as dy by v, that is equal to dx by u, or u dy minus v dx equal to 0. So which represents the differential equation of the streamline in two-dimensional flow. For a streamline is concerned, the component of the velocity in tangential direction only. So there is no component of the velocity in the normal direction. So that means flow that is always taking place along the streamline. There is no flow across the streamline. For a three-dimensional flow is concerned, the differential equation of the streamline can be written as dx by u, that is equal to dy by v, that is equal to dz by w. So remember, streamline gives the direction of motion of the particle at each point. Since the velocity vector at all points are tangential to the streamline, there can be no flow across the streamline. So this is very important concept to be used for the analysis of the flow. Now by analyzing the streamlines, we can identify the type of flow. For example, for a steady uniform flow is concerned, that is, steady uniform flow means the flow characteristics are constant with respect to space and time. So let us consider the flow through a pipe. So this pipe is running full, and since the flow is steady uniform, at every point the flow characteristics are same. Or in other words, for a steady uniform flow, streamlines are straight or they are parallel. Similarly, in the case of non-uniform flow, for example, suppose we allow the flow to flow through a divergent cone. So here the streamlines are getting diverged. Similarly, in the case of convergent cone, streamlines are getting converged, which shows that streamlines are closely follows the solid boundaries. Solid boundaries of flow represents the surface containing streamlines. Now let us work out a problem relating the equation of streamline. So velocity distribution of three-dimensional flow is given as u equal to minus x, v equal to 2y and w equal to 3 minus z. So find the equation of streamline passing through a point 1, 1, 2. So differential equation of streamline representing three-dimensional flow, that is equal to dx by u equal to dy by v equal to dz by w. So by substituting the corresponding values of u, v and w as u equal to minus x, v equal to 2y and w equal to 3 minus z, this equation can be modified as dx by minus x equal to dy by 2y equal to dz by 3 minus z. This consists of two independent set of equations. One is dx by minus x equal to dy by 2y and another is dx by minus x equal to dz by 3 minus z. Considering the first set of equation, that is dx by minus x equal to dy by 2y. So if you are integrating this expression, you are ending with minus log x equal to half into log y plus c1. If you are substituting the value of x and y as x equal to 1 and y equal to 1, then the value of c1, that is equal to 0. So if you are rewriting this expression, you will get as x raised to minus 1 equal to root y. Now consider other independent equation as dx by minus x equal to dz by 3 minus z. So if you are integrating, you are ending with minus log x equal to minus log of 3 minus z plus c2. If you are substituting the value of x and z as x equal to 1 and z equal to 2, then the value of constant c2, that is equal to 0, or we can rewrite this expression as x raised to minus 1 equal to 3 minus z raised to minus 1 or x equal to 3 minus z. So if you are equating 1 and 2, then the final expression is x equal to 1 by root y, that is equal to 3 minus z. This also you can solve it separately. So next part is the discussion on Streamtube. Streamtube is an imaginary tube which is composed of streamlines passing through a closed curve. This is a Streamtube which is composed of streamlines. A streamline is concerned, it has the component of velocity in tangential direction only. There is no component of the velocity in the normal direction. So that means there is no flow across the streamline. So the flow that is coming here as inflow and it is going out as outflow. There is no flow across the streamline. So what is the importance of Streamtube? The concept of Streamtube can be extended and the entire flow region may be considered to be composed of innumerable Streamtube or small cross-section. Streamtube may be of any shape, regular or irregular. The solid boundaries of the flow represents the surface containing the streamlines. Now, what is the use of Streamtube? This is very useful concept in dealing with the flow of large body of fluid since it allows the element of the fluid to be isolated for the analysis. Now the session comes to an end. Our next video, that is on equation of continuity, conservation of mass. For the time being it is enough. Thank you.